Hello everyone, I'm Kshitish, a dual degree student at IIT Madras in the Department of Complex System Dynamics. In this video, we will briefly explore my master's thesis project done under the supervision of Professor Danny Raj, which is titled Discovery of Stochastic Hydrodynamic Equations from Ecological Time Series Data Derived from Collective Movement Scenario. Now, flocking birds, schooling fish, herding sheep, these are some of the most visually striking phenomena in nature. What makes them fascinating to a physicist is that this large-scale order emerges purely from local interactions between individuals without any central controller. Studying these systems can give us interesting insights towards developing decentralized artificial swarms. Now, my thesis asks the question, can we discover the equations governing these kind of collective motion? So in a prior study involving equation discovery, researchers were able to extract equations for the polarization order parameter, showing that the multiplicative noise is the driver of collective motion. But when we increase the system size and look at a system with higher number of individuals, we see that the behavior differs on a spatial scale, with different parts of the crowd doing different things at the same time. So this begs the question, can we derive spatially explicit stochastic equation to explain the system? That leads to our objective where we develop a framework for SPDE discovery and analyze how different terms arise as a framework as a result of different interaction regimes. The equation discovery procedure is a two-stage approach, where we first estimate the functional form of the drift equation, which describes the average behavior of the system, and then we estimate the diffusion term, which describes the fluctuations around the drift. For drift discovery, we create the target vector consisting of the time derivatives, which and the candidate matrix is created with spatial derivatives, and then we use sparse regression, to find a functional form of the drift term. For diffusion, we use the estimated drift term to find the residuals, which is then used to build the target vector. Then the candidate library is built using spatial derivatives again, and then we use regression again to get the diffusion term as well. For So first, we move to the validation of the framework, where we first simulate a known SPD. We perform equation discovery on this simulation, and then the equation discovered from the simulation, if it is the same as the known SPD, our framework is verified. So firstly, we use the stochastic heat equation. We discover the drift term, which is quite accurately discovered. Then to test the robustness of the framework, we simulate three cases where the noise term is additive, multiplicative, or the mixed noise. We see that in all three cases, the predicted and the expected coefficient values are quite similar, showing the robustness of the system. Then we move on to the second case, where we take the minimal Tornado equation, which is a paired coupled SPDE, and we simulate the system, and we find that the density and polarization drift are quite accurately discovered with some mismatch in the coefficients, but the diffusion fit is bad, even though the sparse equation discovered is pretty good. Then now we use this validated framework for discovering of density PDE and polarization SPD for particle data derived from Vic-check simulation. The particle simulation is first coarse-grained to produce a field data, which is then used by the framework to discover the equation. The density equation is discovered to be the continuity mass conservation. The density equation is discovered to be the continuity mass conservation equation with the coefficient equal to the fixed agent velocity in the model. The drift equation discovered has a decent fit, and it matches the Tornado description, which was derived for the Vic-check model analytically. While the diffusion has a bad fit, but it is still a sparse equation. Now, we use this framework to discover equations for three cases with different interaction regimes, namely pairwise, ternary, and Vic-check-like. On comparing equations discovered in these cases with the Vic-check model, we see that the sum terms show up in all cases with similar coefficients, showing that the baseline terms for active matter simulations are quite common, while we also see that the coefficient of Laplacian term increases as the information term increases. Conclusion, that concludes the project, where we developed a framework and validated it by successfully discovering the known equations. We use this framework then to compare equations between four cases, giving us insight into the baseline physics and information transfer. Thank you.